Okay, so this video deals with slightly more advanced theory behind generating signals in NMR spectroscopy. It builds on the previous video on basic theory, where we got to this stage here. So if this looks in any way confusing, then go and look at the previous video. I'll put a link to that in the description. As a little caveat before we start, I'm not an NMR spectroscopist, and I won't go sort of heavily into the theory behind NMR spectroscopy, but this level of theory is sufficient for our final year Advanced Organic Synthesis and Spectroscopy course. So in the previous video, we covered how nuclei, when they're placed in an applied magnetic field B0, will organise themselves into a number of spin states, and for a spin-and-a-half nuclei, that's two states, which are a low energy state that's aligned with the magnetic field, or a high energy state that's aligned against the magnetic field. And the gap between these two energy states we call delta E, or the gap in energy. So delta E is given by the equation here, so delta E equals h times gamma times B0 over 2 pi, where h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Gamma is the gyromagnetic ratio, sometimes called the magnetogyric ratio. This is essentially a measure of how a particular type of nucleus responds to magnetic fields. So each nucleus, like 1 hydrogen, 2 hydrogen, 13 carbon, and so on, will have their own gyromagnetic ratio. And B0 is the strength of the applied magnetic field. That's the field that's being applied by the spectrometer, and that's measured in Tesla. So to calculate delta E as an example for a proton nucleus in a 5.87 Tesla applied magnetic field, we simply feed all of the values that we have over here into the equation. So here I've given you the gyromagnetic ratio for a proton, which is 267.512 times 10 to the 6 radians per Tesla per second. So by feeding that all in, we get to this, and that gives us an overall answer of 1.66 times 10 to the minus 25 joules, which is not a large amount of energy at all. So if we think about populations of nuclei, and there will always be a relatively large population of nuclei that we're analysing in NMR spectroscopy, there will always be more nuclei in the low energy spin state than the high energy spin state. This is given by a Boltzmann distribution. So I've represented this here. Here we have 6 nuclei in the low energy spin state and 2 nuclei in the high energy spin state, just as an easily processable example. This population excess gives rise to something called the bulk magnetization, and we'll come back to this idea later on. But basically we have an overall excess of one spin state over another, which is giving us this bulk magnetization factor here. So if we take our NMR sample and we pulse radio frequency radiation at it, that energy from the radio frequency radiation can be absorbed, and that can promote one of our nuclei from the low energy spin state to the high energy spin state. That gives us a new population of nuclei over here, and we can continue to pulse RF radiation at our sample and keep promoting nuclei from the low energy spin state to the high energy spin state, as long as there is an excess of nuclei in the low energy spin state. As soon as we reach this situation over here where we have our populations equal, and in this case it's exemplified by having 4 nuclei in each energy level now, this is what we call saturation. And saturation means that our sample can no longer absorb net amounts of RF radiation energy. If we take a sample which has reached saturation point, so our populations are both equal, and we try to apply more RF radiation energy to it, there is an equal probability that a nucleus will be promoted from the low energy state to the high energy state by absorption, as there is a nucleus will be demoted from the high energy state to the low energy state in a process called stimulated emission. And because each of these pathways are equally likely, we have no net absorption of energy overall. And as I said before, this is what we call a saturated system, and this sort of system can no longer give us any information in an NMR spectrum. So we have to stop applying RF radiation at this point. So we said previously that in any system at equilibrium there will always be more nuclei in the low energy state than the high energy state. So all we need to do basically is allow the system to return to the Boltzmann equilibrium. So by just allowing the system to relax, some of our high energy nuclei are returning to the low energy state through a process called spin lattice relaxation. So if we give our sample long enough, it will eventually return to a system where we have a bulk magnetization and it's no longer saturated. And the amount of time that it takes for this relaxation process to occur is called T1, or the spin lattice relaxation time. And T1 will depend on a number of different factors, the system that you're using, the nuclei that you're analysing, and so on. So the more nuclei we can convert from the low energy state to the high energy state, the stronger our NMR signal will become. But as we've seen, eventually the system will saturate. So how do we get around this? Well, if we allow the sample to relax between multiple RF pulses, we can combine and average the data. So if we treat this system with RF radiation until it reaches a point of either saturation or subsaturation, we allow the sample to relax through the spin lattice relaxation time, we can then hit it again with RF radiation, because we've now got our bulk magnetization returned and we can continue to collect data. And if we continue to do this in a continuous sequence, we can combine and average the data that we get, which will lead to a better signal to noise ratio. Now this idea of pulsing and then allowing to relax and then pulsing again and averaging the data takes the form of a pulse sequence, and quite often you'll see it represented like this, where we have our RF pulse here, we have a small amount of dead time, and then we start to collect our NMR signal, which is the acquisition time over here. We then have an interpulse delay, and then we hit it with an RF pulse again, and we repeat. So this is allowing enough time for our nuclei to relax, back to equilibrium again before we hit it with the next RF pulse. So by performing multiple acquisitions and averaging the data, this improves our signal to noise ratio. So this is an example of an NMR signal which has a low signal to noise ratio. We can see that the noise down here represents a substantial portion of the signal. If we do more scans and we average the data, eventually the noise will cancel itself out and the signal will reinforce itself. So we can also improve our signal to noise ratio and the strength of our NMR signal in general by having a larger population excess. If we have a larger population excess, we can promote more nuclei before saturation occurs. So therefore we can generate more data from a single RF pulse before we have to let the sample relax. So it's obviously in our best interest to ensure that the population excess is as large as possible. So how large is it? Well, the relative number of nuclei that we have in our low and high energy states is given by a Boltzmann distribution, as we discussed before. So number of nuclei in the high energy state divided by number of nuclei in the low energy state is equal to e to the power minus delta E, which is the gap between the energy levels, divided by kT, where K is the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin, and T is the temperature in Kelvin. So, as an example, at 298 K, which is roughly room temperature, what's the ratio of proton nuclei in the low and high energy spin states in a 5.87 Tesla magnetic field? Well, we calculated delta E previously, and by feeding in the rest of the information that we have here, we come up with this equation here, which gives us e to the power minus 4.04 times 10 to the minus 5, which is equal to 0.99996. So now if we want to express this value as a ratio, we can simply rearrange the equation. We know that n high over n low equals 0.99996. We also know that n high plus n low must equal 1, because that's our entire sample size. So by rearranging the equation as follows, we end up with n low equals 0.50001. N high must equal 1 minus n low, so therefore n high equals 0.49999. So we can actually think about this as the low energy state being 50.001% and the high energy state being 49.999% of the nuclei. So the pictorial representation that we had is actually a massive overestimate, where we've got 6 nuclei in the low energy state and 2 nuclei in the high energy state. Actually, it's 50.001 in the low energy state and 49.999 in the high. This is 1 in 50,000, which is about 20 parts per million. Obviously, that's dependent on the nucleus, the magnetic field strength, and the temperature. So we can increase our population excess. We can make our NMR experiment more sensitive by lowering the temperature, because this equation is dependent on temperature over here. We can increase delta E because delta E takes part up here, and we can increase delta E by analysing nuclei with a larger gyromagnetic ratio. Obviously that's not a super efficient way of doing things because we still want to look at protons, but we can also increase the applied field strength, so we can use a stronger spectrometer and that will give us more sensitive NMR spectra. So I mentioned previously that in order to undergo spin flip, nuclei can only absorb a specific amount of energy which corresponds to delta E. So if your energy of your incoming RF pulse doesn't match delta E, it's not absorbed. It has to match exactly. Since E equals h nu, only a specific frequency is therefore absorbed because they're linked in this equation by Planck's constant. So the specific frequency that can be absorbed is called the resonance frequency or the Larmor frequency, and we're giving it the designator nu here, and it's given by this equation here. So as an example, calculating the resonance frequency of proton nuclei, again in a 5.87 Tesla magnetic field. We know the gyromagnetic ratio for proton because we were given it earlier, and we know what pi is, and our B0, our applied field, is 5.87. So if we feed everything in, we get this, and that gives us a resonance frequency of 250,047,045 per seconds. Since per second is hertz, that's 250 megahertz. So NMR spectrometers are usually described in terms of their resonance frequency for proton nuclei. So the 5.87 Tesla magnet we actually call a 250 megahertz spectrometer, but you'll see this written on the outside of the spectrometer that you're using, so the 300, 400, 600 and 850. These are the resonance frequencies for a proton nucleus in that particular spectrometer, but they will all have increasing magnetic field strengths going from 300 up to 850. So as an aside, the same spectrometer causes carbon nuclei to resonate at a different frequency. The gyromagnetic ratio of carbon is almost exactly 4 times smaller than that of proton. So if you have a 400 megahertz proton instrument, it will cause carbon-13 nuclei to resonate at 100 megahertz, and so on. And that's simply because the gyromagnetic ratio of carbon is different. So our spectrometer at Sheffield Hallam University is a 400 megahertz instrument. How strong is the magnetic field? Well, we can reverse engineer this equation here, which is giving us the Larmor frequency, where we get 1 over B0 is equal to the gyromagnetic ratio divided by the Larmor frequency times by 2 pi. So if we feed in all of our data here, we know our gyromagnetic ratio, we have our megahertz rating of our instrument, and then 2 times pi. We end up with 1 over B0 is equal to 0.106 and so on per Tesla. And then by rearranging that, we end up with B0 is equal to 9.39 Tesla. So our instrument is a 9.39 Tesla magnet, but we commonly call that a 400 megahertz instrument because that's the resonance frequency for a proton. So, in addition to our incoming RF radiation having to match the resonance frequency, there's also a requirement that the nucleus has to have an oscillating magnetic moment before it can absorb energy. So where does this oscillating magnetic moment arise from? Well, nuclei aren't spinning in the normal sense, but we often think of them that way because it's helpful. So if we look at this nucleus here, it's spinning on its axis like this. Spinning objects rarely spin perfectly on their axes, right? They wobble, and this is a process called precession. So if you ever spun a spinning top, you will know that the top is itself spinning on its axis, but the top of the axis over here you can see is moving in a circle, and this is what we call precession. So our nucleus is spinning on its axis, but actually it's not spinning perfectly on its axis. The magnetic moment is spinning around in a circle, or it's precessing around in a circle, and that's precessing around the z-axis at the resonance frequency. So this precession is occurring at the Larmor frequency, or the resonance frequency. So we could measure this in our xy plane. So we've said that the magnetic moment is spinning around the z-axis. This is causing a signal positive y, negative y, positive y, negative y, and so on, and the same in the x-axis. We could measure this as our NMR signal, but we have a problem with that. So our individual nuclei are all processing at the resonance frequency. They are all processing the same number of times per second, but our entire sample now, we're considering 8 atoms here, they're doing so in a disordered way. So as they process, you can see that they're all at different stages of the orbit. And if we overlay a snapshot of the entire sample and continue to process, you'll notice that the average never changes. There's always one arrow at each particular location. Now, this is where our bulk magnetization comes in. So if we average all of these black arrows around here, we end up with something which is facing in this direction, but it's dead in the center of this arrow here. It never actually tips off of the z-axis. So the bulk magnetization is the average of all of the individual magnetic moments which make up our entire sample. And in this simplistic case, we've only got 8 nuclei. So it's the average of what these 8 nuclei are doing. So if the bulk magnetization never tips off the z-axis, we don't read a signal in the x and y axes. So what happens now? Our RF radiation comes in and we hit our sample with an RF pulse, and this has the effect of knocking all of our precessions into alignment. Like that. So now if we take an average of this, we'll find that all of our arrows have tipped over to one side. And the average of all of those arrows, the bulk magnetization, will now tip off of its axis. And as we continue to process, our nuclei are now processing in a coherent way. They're all at the same phase of their precession. They're all processing in coherence. And as a result, our bulk magnetization, as well as tipping off its axis, it now starts to process in the XY plane. So after our RF pulse is turned off, the precession of the individual nuclei becomes disordered. And this is a second time parameter called T2. So over time, this eventually causes our bulk magnetization to return to the z-axis. So as our nuclei become disordered over time, the bulk magnetization gets smaller and smaller until it eventually returns to the z-axis. This process is called spin-spin relaxation, and the spin-spin relaxation time, the amount of time that this takes, is called T2. So this is distinct from our spin lattice relaxation, or T1. So as the bulk magnetization spirals around the z-axis during T2, we can detect this in the y-axis. So we said before that if you move an electrical charge, it generates a magnetic moment. Well, if we have a moving magnetic moment, it will generate an electrical charge. And we can detect this in the y-axis. So as our bulk magnetization spirals around the z-axis, it goes from being highly positive y to highly negative y, positive y, negative y, positive y, and so on. So we'll read that as a signal like this that eventually decays over time. And this is our actual NMR signal. This is what we're detecting from our spectrometer. So this NMR signal is a measurement of frequency over time, and this is what we call the free induction decay. This is raw NMR data. What we then do is treat it with a mathematical equation called the Fourier Transform, and that converts our spectrum in the time domain to a spectrum in the frequency domain. So this free induction decay over here correlates to a single frequency, and that will give us a single peak on our frequency domain NMR spectrum, which is the one that we recognize as being an NMR spectrum. This is a real free induction decay, so they're obviously much more complicated than that. But by Fourier transforming the signal, we basically get a multitude of different signals, which are all resonating at slightly different frequencies. So this is a real example, but the computer will basically figure everything out for us by doing a Fourier transform, and we end up with something that looks more like a normal NMR spectrum. So if we consider both spin states in this model, we can see why saturation of the system gives us no further information. So we said that there was a loss in the bulk magnetization once our energy states become equally populated. Well, if we consider our downspins as well as our upspins in this example, So on this this nucleus over here, we have 5 upspins and 3 downspins. So we have an overall bulk magnetization, which is pointing in this direction, because there are 5 spins up here and only 3 down here. So therefore it's pointing out of this side of the nucleus. So we have bulk magnetization in the up direction. If we pulse RF radiation at this and we convert one of our upspins into a downspin, we now have an equal amount of both. And because these upspins and these downspins are equally balanced out, our bulk magnetization now is somewhere in the core of the nucleus. So it's no longer pointing in a definite direction and precessing around the y-axis. It's now sitting right in the middle of the nucleus, so we cannot detect it in the x or y-axes. So this is just a pictorial representation of why saturation is not giving us any further information in this NMR spectrum.